Very good morning and welcome to the fourth lecture on multivariate inferential statistics. Today we discuss hypothesis testing for equality of two population mean vectors. You all know what is meant by two population and also two population mean vectors. We discuss different sampling scenarios and example will be given. I am sure you have enjoyed this week lectures and today's lectures also equally important for you and you will enjoy it. Let us see the next what is there for you.
Now, what will happen if you go for difference in two population means? Getting me? How do you proceed? You have done in univariate case, yes or no? We say that we want to test the equality of two population means. I think you please remember your univariate case. There are two variables x1 and x2 and you computed x1 bar and x2 bar. You also computed S1 and S2. You may be knowing the sigma 1 and sigma 2 depending on the situation. You have created a random variable which is x1 bar minus x2 bar. You recollect your lecture on test of equality of two population mean under univariate situation. This is a random variable. Now, this random variable there will be expected value, that is mu 1 minus mu 2, and there will be variance. You have seen that this is variance x 1 bar plus variance x 2 bar. So, that one we have seen that this is variance means sigma square by n 1 plus sigma 2 square by n 2, where n 1 sample from population 1 and n 2 sample from population 2. What is multivariate counterpart of this? Getting me? What will happen? Your random variable will be a random vector x1 bar minus x2 bar. This is a random, your random variable is this variable vector. Yes, and your population is like this. So, what happened, your x1 bar from the first population, x2 bar from the second population, again these are all p variable case. Then you have computed S1, you have computed S2. What are these things? Covariance matrix for population 1, covariance matrix for population 2, and you know that suppose the first one is n1 or n2. Okay. So, I will give different notation, I will give A and B because I have developed in like this A and B, A and okay. The slide I prepared using A and B notation. I am asking you find out the expected value of x1 bar minus x2 bar, last bench here, that side. Idea? Any idea? What I said? Expected value will be this for univariate case. Multivariate case also will be the same thing, but only vector notation. So, that means expected value of x1 bar minus x2 bar, that is nothing but mu 1 minus mu 2. How many variables are there? There are p variables. So, this will be a quantity like this. Suppose mu 1 1 minus that, I think I will give A, then that will be better. I told you x bar minus this bar mu A minus mu B, then this is mu A1, mu B1, mu A2 minus mu B2, like this, mu AP minus mu BP. So, those who were absent in univariate class, for them it is difficult to grasp, and you will never learn, because you have missed the vital issues already. Then what will be the variance part? X A bar minus X B bar, that will be variance of X A bar plus variance of X B bar. I have shown you in multivariate univariate case, variance of this is this. Forget about how this derivation, all those things are coming, because we are not statistical expert, we are users. So, then if sigma square is the variance for the univariate case, we all have seen that capital sigma is the counterpart in multivariate case. So, if it is A, this will also be A. If this one is B, I will go by this. So, this one will be sigma A by N A, because you have seen earlier that from population on N1 and N2 is divided, I am now denoting by A and B, and this will be your sigma B by NB. Okay. Now, you think what will happen? I want to create Z. What is the approach? Z approach is, you first write down the random variable minus its expected value divided by square of its variance. So, I can write down here very clearly what is my random variable, x1 bar minus x2 bar. So, let us write x1 bar xa bar minus xb bar minus expected value means mu a minus mu b divided by, you can write down the variance component sigma a by Na plus sigma b by Nb. Now, see, this is in the multivariate domain, and you have already seen in univariate case that similar things you have created when I have written like this, A transpose x bar minus A transpose mu by that square root of A transpose sigma A by N. This is for only one population case. That means, similar analog has to be created for difference also. Please remember, here is one random variable vector, that is x1 bar minus x2 bar. Although you are taking sample from two population, finally you are creating one random variable vector x1 bar, xa bar and xb bar, xa bar and xb bar. Okay. So, the same principle will be applied now. Only thing is that one more component added by denoting sigma A, sigma B, your later on we will be adding SA, SB, something like this, but essentially other things remain same. So, you have similar situation here. You are sampling from multivariate normal populations with known sigma 1 and sigma 2. You ask some question, otherwise it will be one sided game. You go through this slide first. Is there any problem in understanding the three scenarios?
So the two populations are independent?
Independent. So, scenario 1, scenario 2 and scenario 3, here first one is like this, that sampling from multivariate normal population known sigma 1 sigma 2, sampling from multivariate normal population with small sample size, unequal, unknown but equal sigma, not unequal, unknown but equal sigma, and sampling from multivariate normal population with large sample size and unknown sigma 1 and sigma 2. We will discuss the second one, because that one you will be using more frequently. Now, in univariate case, again you recall that we said that if sigma 1 square equal to sigma 2 square equal to sigma square, then we have used certain estimate of sigma or sigma square. What is this? We say SP square. Can you remember that we say a square pooled? I think you can remember there we have used that n1 minus 1 S1 plus n2 minus 1 S2 by n1 plus n2 minus 2. Here we will use the same thing. Here what is our case? Sigma A is sigma B equal to sigma. This is our case. We will be creating similar S-pooled covariance matrix, and that will be NA minus 1 SA plus NB minus 1 SB divided by NA plus NB minus 2. Okay. So, that this one is our estimate of sigma. Okay. Now, let us see some of the slides first, and we will explain, and there is the same way that confidence region first, followed by your simultaneous confidence interval, but please understand in totality we are repeating what we have developed so far in univariate your single population, single multivariate population case. We are repeating this one. The random variable is changing. Okay. If you do not understand this, so I am repeating it also several times. I am saying the random variable is changing, accordingly the statistics, that total formulation is changing. Otherwise, the statistic, that the t square statistics, again the A for chi-square distribution, those things remain same. Your change is in terms of computation here. You see this slide and have a feel of it. Small sample case. All those things available in Wichan book, Johnson and Wichan book, but they have used some other notation, not A B, maybe they have used 1 and 2, something like this. What I am saying here, my condition is like this, that you are sampling from multivariate normal population. There are two such populations, XA, NP, mu A and sigma A, XB, that is again NP, mu B, sigma B, and your population covariance matrix, both the matrices are equal to sigma. And your sample statistics is, what is my random variable? X A bar minus X B bar. this minus its expected value. Please get the connection, link point. We said the random variable minus its mean expected value. So, expected value of x bar a and minus x bar b, that will be mu a minus mu b. In the single population case, you have used the formula for t square x bar minus mu transpose. Now, no longer you are using x bar, you are using the difference between two population mean vector. So, x a bar minus x b bar, that is similar to x bar, analog to single population, that is x bar minus mean, that transpose. Then followed by what happened, there you have used S inverse, here you have two population case. So, and sigma a equal to sigma b equal to sigma. So, you are calculating the S pooled first. This S pooled is this one by N a plus 1 by N b into S pooled. S pooled is the same equation what you have seen earlier. What is S pooled here? N a minus 1 into S a plus N b minus 1 into S b divided by N a plus N b minus 2. So, you are writing this, and you know that earlier we also derived in univariate case that 1 by N 1 plus 1 by N 2, that quantity will be there. So, this is what is the very covariance part. So, you have to take the inverse of this covariance, then you square this one x a bar minus x b bar, that random variable, that is squaring.
In single population there are around n in the beginning. So n is
Single population?
there was n at the beginning. Then x bar minus
Yes, yes, yes.
but n is
Here n is here.
actually that part is going to
It is coming here n a plus n b, because in earlier case what happened, this is 1 by root n and then n you are taking other side. Variance part in univariate case, what is that? Sigma by root n, scalar quantity, that sigma by root n, that derivation is such that root n is going to the numerator, you are writing. When you are going for hoteling t square, what is happening? There also single population case, that n is there and coming to the numerator and you are writing here n. In this case what is happening, this n is taken care of by 1 by N a plus 1 by N b. See, this n component is coming because of variance. In univariate case, in multivariate case because of covariance. When it is single population, you do not have any problem, this square n component will come here, and here it is the two population difference case. So, the variability will be taken by like this, okay, and this is the quantity. This quantity follows what distribution? F distribution again, okay. But you see some other part, the two component is there. In earlier case it was n 1 minus n minus 1 into p by n minus p. What it is written here? N a plus N b minus 2 into p divided by N a plus N b minus p minus 1, that you have to remember, okay. Otherwise, if you want to derive it, very difficult, it will go, you will forget that, okay, I will stop reading this multivariate statistics. This one, and see the f p, p is the numerator degrees of freedom, and N a plus N b minus p minus 1, this is the denominator degrees of freedom, and your confidence region will be t square less than equal to this. We will not repeat this. I hope that you are understanding, I am sure you are understanding. Those who were present earlier, they are understanding, I am sure. Whether you may be, it is maybe sometimes difficult, because so much of these terms mu a, mu b, and n a, n b, all those things, but the concept, the message must be clear to all those who were attending from the beginning. If not, then please ask me question, come to my room, and again you get it clarified. And those who are not attending, forget. That is the large sample, and in large sample case, chi-square distribution you will use. This is for the confidence region. Now, this is one example, and it is the data I have just arbitrarily given, but we have done one study in some of the coal mines. This is a real application I am telling you. These data are not from that real application, but similar application we have done. We have found out that the management was facing problem with managing accident, particularly injuries in underground coal mines. They have gathered lot of data, lot of injury data, means people who were injured, and there are another group who were not injured. Our aim was that whether there is difference in characteristics of that two groups. So, we have taken 24 variables and then we 150 observations each from accident group, from non-accident group. Then that means what is, this is a two group phenomena. I want to test the mean differences between the two population. If there is difference, then we have to find out what are the variables making the difference. That type of study we have done. It is applicable to quality control also. For example, you will find out in Johnson and Johnson one application is given in from the police department activities point of view. That part you please check. So, now suppose this is the case, two population and you are getting x a bar in SA, x b bar, S b like this, and then what you require to do, you first find out the confidence region. Same thing you are doing with more computation, nothing else. So, you are finding out t square, then finding out your what is the your sampling distribution, and you are making this confidence region. Okay. And I ask you to practice, very difficult. If you do not practice, it will be difficult. Multivariate is really complex, but if you go to the theoretical side, then it is, we do not have that background, and but application side even then it is complex. Although we are in the, now we will use the same situation, maximization lemma and Bonferroni approach. Big equations. Okay, big approach. Okay. Now, see that maximization lemma and Bonferroni approach, the difference is coming chi square and z. Then your the second one, equal unequal and unknown case, here you are using this F distribution available in Johnson and Wichan, you do not require to write. Third case, large sample chi-square distribution. You create your example here. Next class I will ask you. There is no example. I thought I am giving, but I find that no, it is better do not give anything. Next class you will be giving one example for this. Arbitrarily I will be asking some of you. Then hypothesis testing. Nirmal, should I stop now? Hypothesis next class I will discuss, or it is okay? Okay. So, you want 1 more hour on hypothesis testing, similar. Okay, then I think this is the end today.